They have a mission that says the mission of the AAVSO is to enable anyone, anywhere, to participate in scientific discovery through variable star astronomy, which sounds like a pretty lofty goal, I guess, but it's what we hope to do with it. So anyway, variable stars in the beginning, Kepler and Brahe, as we know, back in the 1500s, were known to have spotted new stars, which at that time were sort of a confusing thing. What is a new star? But they made records of new stars, which we now call novas. By the 16th century, several stars were known to be variables. Algol, Beta Lyrae, and our Corona Borealis were all known to be variable. Astronomers didn't have much of an idea why they were varying. They understood the concept that maybe they were a binary system with one star passing in front of the other, which would cause the brightness to change, but they couldn't explain several of these patterns. They just weren't easily explained by the binary idea. By 1844, Allanger, a European astronomer, invited amateurs to start observing. He thought it would be important to make records of when they were bright and when they were faint, so that we could sort of keep track of the behavior of the light changes of these stars. But in 1880, the photographic emulsion thing, glass plates with photographic emulsions, became good enough for astronomy. And this was a really big change in astronomy, because now we had a way to make a permanent record of the brightness and the brightness changes that just wasn't possible before that. And interestingly, about that time, Harvard College Observatory set upon a huge task. They decided to photograph, record, and catalog the entire sky, literally everything in the sky. They even found money to put up an observing station in the Southern Hemisphere in Chile with 3 or 4 telescopes. Started collecting glass plates with these telescopes, and actually were observing right from Harvard College Observatory right in Boston, photographing the night sky, because at that time, at the 1900s, the dark sky was still dark, even in Boston, as hard as that is to believe today. And they discovered that with thousands and thousands of glass plates, who's going to do all this recording? If they're going to record brightness, position, and spectral class, my goodness, that's a lot of work. If you're producing thousands of glass plates, how's that going to happen? So Harvard College Observatory, they actually hired a group of about 10 to 15 women. The group changed over the years, but several of them were there the entire time. Several of these ladies became very distinctive. The one lady right in the middle is Wilhelmina Fleming, and also on this picture is Annie Jump Cannon. And these 2 women actually played a major role in establishing the spectral classes of stars off of these glass plates. They got to the point where Wilhelmina Fleming could take a quick look at a glass plate and characterize spectrographically the spectrographic types of stars. She ended up publishing a catalog of 500,000 spectral classes at the end of her career in the 1940s, and it was published in the Harvard archives. People were, in fact, in those days, people didn't recognize women in science, and Harvard College pushed this really hard to get it published. So anyway, these women had a tremendous contribution to make to astronomy in all this work. And in fact, this whole effort is very well told in a book called The Glass Universe by Deva Sobel. I highly recommend the book. She also wrote Galileo's Daughter and Longitude, which are also tremendous books about. Galileo's Daughter is one of the best books I've ever read about that period of time, and Galileo's struggles with trying to understand science and how to tell the world about the science he was discovering. Anyway, Davis Sowell tells the story. So AAVSO had the beginnings because about that time, 1911, the Harvard College Observatory director, Edward Pickering, established the AAVSO. He felt that amateurs could observe these interesting variables. And by golly, by now they knew of about 600 to 800 variable stars that were observable with amateur telescopes. And a well-equipped amateur could go out into his backyard and take a look at these things and record their changes in brightness and send them to the AAVSO headquarters at the Harvard College Observatory. And they had a hired, they called him secretary then. They hired a fella to actually start coordinating the work of all these amateurs, and they started developing charts and developing comparison stars, and the whole beginnings of AAVSO happened in 1911 at Harvard College. And the organization became a separate nonprofit and broke away from Harvard in 1954. So why would you study variable stars? Why would anybody do that? Why would amateur astronomers do that? Well, you might be curious about why they vary. Why do they change, and why are they so different? And we've discovered that studying variables gives you some clues about how stars work. And also, these are observations that professionals won't do or can't do. You know, in the age of big telescopes and sky satellites and all that, a lot of astronomy gets wrapped up in the high energy side of things. And in fact, most of the brighter stars are largely ignored these days. They're ignored by many astronomers. So, and you have the advantage in that you are the owner of your telescope and you control what gets looked at, whereas professional astronomers don't have that choice. They have to plead for time at the observatory, and then they have very limited time available to do their study. So amateurs can participate very strongly in this area. A little refresher about stellar interiors. We know that the central core of a general population main sequence star has a core. It's about 15 million degrees Kelvin. This is a thermonuclear bomb sitting in the middle of the sun. It's held in place by its own gravity. There's so much material there that the gravity keeps it compressed into that one central ball. The radiation that emits out of it can take hundreds of thousands of years to reach the surface and be emitted as starlight that we see. I also point out on this diagram that it shows convection zones out near the outer part of the star. You can see those red circles that are drawn there. Those are layers where the star, the material is cooling, and as it cools, it starts setting up these cycles of convection layers. And this diagram shows 3 separate convection layers at the upper part of the diagram there. So we'll be referring to some of these things a little later, so I pointed out now to remind you about what the interior of these stars look like. It's also important to understand that most stars are parts of groups. They're either in clusters like the upper left picture there, or the lower left picture there is a binary star, 2 stars that are very close together. You can see the spikes off those 2 stars. And then of course we all know about the double star that's around Tatooine that's made it so popular in Star Wars. I was listening to an astronomer talk that was talking about binaries, and he said 4 out of 3 stars are actually binaries. So I kind of wondered about his math, but the point being that single stars like our sun are actually not rare, but they're also as often part of binary systems and not just single stars. I'll also give you a little bit of a reminder about the evolution of stars because variables play into this picture. And on the upper part of the graph, you take a small star like our sun. Our sun is considered a dwarf. It's a large dwarf, but it's still in the dwarf end of things on the H&R diagram. And as it evolves, it will turn into a red giant. The core of the star will start to cool off as it burns up its energy, and the star will grow. We were talking about that a little bit earlier in the chat part of this evening. The sun will grow. There'll be a time when the sun is, we think of the sun now as when it rises in the east, it's about the size of your thumb at arm's length. There'll be a time when the sun covers most of the eastern horizon on Earth. Of course, life will be long gone by then because it will have just boiled away from the heat of the growing sun. As that grows, the outer layers of the star start to peel away and create a planetary nebula that we know of so commonly. And eventually it just dwindles away to a white dwarf. A white dwarf doesn't actually produce new light. The fusion has stopped. A white dwarf is still hot. It's still like 50,000 degrees, but it's not creating any new energy by fusion. All of that has now stopped. If you look at the lower part of the graph, over on the left, you start off with a somewhat larger star that's maybe 2 or 3 or 5 or 6 times bigger than the sun. It will grow to a red supergiant as it starts to die. And as its core contracts, because it's burning up its fuel, it starts to contract under its own gravity. It will turn into a type 2 supernova. And after that supernova gets done, the only things left is either a neutron star, which is only about the size of a large city, really tiny, or diminishes right into a black hole, depending on how large the star was to begin with. So there's 2 evolutionary paths, and variable stars fit in at various points along these evolutionary paths. So what types of variables am I going to talk about tonight? Well, we're going to talk about eclipsing binaries. There's lots of them out there. The AAVSO tracks hundreds of them. There are a bunch of pulsators, and there are thousands of pulsators of various types. And cataclysmics. My goodness, what is a cataclysmic variable? That sounds like something terrible happened. But it turns out there's whole classes of cataclysmics of great interest to amateurs. So anyway, we'll start with eclipsing binaries. Algol is the one most people have heard of, very famous. It's a binary system, 2 stars rotating around each other. And over here on the upper left part of the diagram, you see one of them is a B star. That's a very hot star. And around it is going a K star, which might be actually larger in size, but it's much cooler and much fainter. And as they go around each other, one of the other is in front of the other. As you see on the upper right corner, the Algol B, the dimmer star, is in front. And when it covers up the bright star, you get, well, let me draw your attention to the lower left corner. And this is what they call a light curve. And on the bottom of the graph, you see the time. In this case, it's in days. And on the y-axis of the graph, the up and down side, we have magnitude. So you can see how the magnitude is changing over a period of time. So when you have one eclipse, when the brighter star is being eclipsed, there's a big drop in brightness. And then when the dimmer star is being eclipsed, there's a smaller change in brightness. That's on the green graph. You see how one of them is just a little dip, and one of them is quite a very sharp drop in brightness. So this is a very noticeable. Eclipsing binaries are very well studied because it lets you understand the science of one thing about how big the stars are, and the peaks, or I should say the minimum light difference at the bottom, lets you determine the period of rotation. How fast are these things rotating around one another? So a lot of science can be taken from studying this green graph and how it changes over time. Now we're going to go on and look at pulsating stars, and you can see the upper picture shows a star at one brightness, and my gosh, on the lower picture, it appears to be much brighter. What in the world happened? Why did it make a change like that? Well, the first group that I'm going to talk about are called long period variables, or Mira stars. Mira is a common name for a star that's down in Cetus, Omicron Ceti. Omicron has a whole different usage these days, but it's a Greek alphabet letter. It's called Mira, and Mira is an Arabic word that means the beautiful. And it was discovered when some European astronomers were drawing star charts, and they drew Mira on the chart and then came back a year later, and my goodness, the star was gone. They couldn't see it. So what in the world happened to Mira? This is a chart of a Mira class star, and you'll see on the time scale on the bottom, it goes from 2001 to 2011. So that's a 10-year period. And on the left side, the up and down scale goes from 8th magnitude to 16th magnitude. And this star is changing from about a little over 9th magnitude down to about 14th magnitude. And it's changing over a period of about 400 days, 450 days maybe. So this obviously can't be explained by something going in front of one star going in front of another, especially when you've got this fairly even uniform curve. This is an entirely different type of behavior. You'll probably also notice that the peaks of the curve are different. Not every one of them is a smooth peak. Some of the peaks are sharper and some of the peaks are broader.
Bill, sorry,
yes.
this is Raj. Just to clarify, the star for that graph, that's not Mira itself, that's LX Cygni, is that right?
That's LX Cygni, I'm sorry. It is a long period class. It is, and it's called a Mira class star, but it's not Mira itself. I'm sorry, yes.
I was a little confused because these visual magnitudes would not be seen with the naked eye, whereas Mira is a naked eye.
No, Mira goes from about 3rd magnitude to about 8th magnitude. Well, 4th magnitude to about 8th magnitude.
All right, sorry for that, but I just want to do a clarify.
No, okay, good point. This is LX Cygni, and when I say Cygni, that's not a mistake. That's actually the possessive form of the pronoun, so that means that it belongs to the constellation Cygnus, LX Cygni. So anyway, this is a very different behavior, and I'll also point out that every red dot that you see is the result of an amateur observation. There's no professional observations here. This is all AAVSO data done by amateur astronomers in their backyards with their personal telescopes. They've gone out and looked at this thing and recorded the brightness changes. Okay, we know now that Miras are dying red supergiants, either from 0.6 up to about 2 solar masses. They're dying red supergiant stars. Remember the graph that we showed of super red giants? They have a period from about 200 to about, maybe 1,000 days. They have a magnitude range from about 2.5 magnitudes to about 5 magnitudes. LX Cygni was about 5.5. Some of them are less than that. They have huge outer shells. You remember the diagram of the stellar interior where the core was 1/4 of the diameter of the star? Well, in the case of a long period variable Mira star, if the core were the size of a walnut, the outer shell would be the size of a high school gymnasium. So it's not hard to see how those outer shells are just sort of willowing away from the star. They're losing about an Earth mass every year. It just wanders away from the outer shells. This was a picture of Myra that I found on a NASA website. It just was absolutely just stunning. Of course, it looks like the star is traveling through space and leaving a trail behind it, but that's not actually what's happening. This is the star is actually stationary, and much of the material in this case was being pushed away to the side. You can see there's some actual bubbles on the right-hand side to go up to almost the upper part of this picture. So anyway, this is most of the material is being pushed away to the left side. At least that's what shows up in this photograph, and that's part of the mass that's just being peeled away from the outer bands of this star. Anyway, impressive photograph. I was just starstruck when I saw the thing. Next type is the Cepheid variables, and this light curve looks very different. It's, first of all, it's only over a period of about 30 days. The period of variation is only 15 days from peak to peak or from valley to valley. And the oscillation is from 9th magnitude down to almost 10th magnitude. So it changes in brightness only about 1 magnitude, but it's got a pretty distinct pattern to it. It's got a pretty sharp rise and a pretty sharp drop and a very narrow top and a very narrow bottom. So this is very different than the Myra that we looked at just a little bit ago. It turns out that Cepheids are yellow supergiants. They are not even on the Hertzsprung-Russell main sequence. They're up in the upper right part of the Hertzsprung-Russell diagram, up in what's called the instability strip. And they're up there with LL Lyra and a bunch of other stars that are known to be unstable. They have periods from 0.6 days to 40 days. So you can see this would be a hard one to watch. If it was 0.6 days, it's going to go through its whole cycle in less than 1 night. If it's 40 days, well, you probably have a chance to see it. But the magnitude range is only 1 magnitude, up to about a magnitude. So these are harder to observe. Shapley, back in the early part of the 20th century, tied together the period, the color changes, and the radial velocity changes, and actually was the first astronomer to describe this as pulsation. People didn't know what it was prior, and Shapley proposed it to be the radial velocity, especially because that in the spectrograph you can see there's times when the star's material is moving towards us and times when it's moving away from us, less than before. So he tied those strings together in a seminal paper that described the pulsation of Cepheids. And interestingly, those outer shells, you remember that diagram that we talked about with those outer shells? The helium ionization is occurring in those outer shells. And the ionization is heating and cooling, causing the outer shells to do this pulsation. And that's what causes these variable stars to change in brightness. So the whole star doesn't pulse, it's just the outer shells that are changing. But guess what? We're back to Harvard College and the Harvard College ladies, because this lady, Henrietta Leavitt, had a huge impact on astronomy. She actually started recording variable stars and took a very big interest. You remember the diagram of the ladies at Harvard? Well, she was one of those women. And she started recording brightnesses of variable stars and started looking at Cepheids in particular. There's a picture of all the ledger books that they kept their records in. They obviously didn't have digital computers in those days. So they all kept records in these ledger books. I just can't imagine how you would keep track of tens of thousands of stars. You have to carry a bunch of that around in your head. Anyway, she became particularly interested in 1600 variable stars in the Magellanic Clouds. And she started to find herself interested in the Magellanic Clouds. I took this picture from out of sky and telescope a couple of years ago. It's just amazing what you can do with DSLR or modern imaging tools. It shows the Magellanic Clouds. The large and small Magellanic Clouds are on the right side of the picture there. They're actually little subgalaxies adjacent to the Milky Way. And the interesting thing about the Magellanic Clouds is that all of their variables are the same distance away, virtually the same distance away. You know, unlike Cepheids that are scattered around the Milky Way, you don't know how far away they are. But in the case of the Magellanic Clouds, they're all about the same distance away, which is a tremendous notion of why they become distinctive. Anyway, back to Henrietta Leavitt and her 1600 variable stars. She noticed that among the Cepheids in the Magellanic Clouds, that the brighter Cepheids had longer periods. And this was a huge change in the early 20th century in astronomy. This was a thunderclap in astronomy, because it meant that if you could measure the period of a Cepheid variable, you also would have a clue about what its absolute brightness was. So then right away, professional astronomers around the world, Hubble included, Harlow Shapley included, began to study Cepheids and studying their periods very carefully so that they could gauge what their brightness must be. This was so important that now in the 21st century, back in 2006, the International Astronomical Union has agreed to now refer to this as Leavitt's law. This was such a big change in the scale of astronomy. It was what led Hubble to finally begin to resolve that the spiral nebulae were separate galaxies. And in Hubble's time, in the 1930s and the 1940s, people thought, Shapley, for example, thought that the Milky Way was the universe and that all the spiral nebula were just artifacts surrounding the Milky Way, just like globular clusters. And so they weren't of much interest to Shapley. But Hubble studied all this and realized, he began to look at Cepheids in close by nearby galaxies and realized they were way farther away than just in the neighborhood of the Milky Way. So anyway, it just fundamentally changed our view of the universe. In fact, Hubble wrote a letter to Shapley in the early 20s before he published his work. And Hubble, as Shapley is known in his office in Cambridge, to read the letter and hold the letter up and say, "This is the letter that destroyed my universe." The Milky Way was no longer just a universe. One of the 5 original justifications to build the Hubble Space Telescope would be the ability to measure Cepheids at 100 in galaxies 100 million light years distance. So I don't know about you, but that just staggers my imagination, measuring the period of a variable star, a Cepheid variable, in a galaxy 100 million light years away. Gaia, the European Space Agency satellite, has identified 6,000 new Cepheids in the Milky Way. And in fact, they've encouraged the AAVSO to start looking at these as a way to improve the quality of the baseline on Cepheids, so that as they continue to work Cepheids, they can improve the baseline about what we know about the luminosity and the periods. And interestingly, those that take Sky and Telescope magazine, the December issue, Henrietta Leavitt is the feature cover article, again written by Davis Sobel, on the life of Henrietta Leavitt. A very, very good story. I encourage, if you don't have it, to find it and read it. It's very interesting. Now we're going to move on to cataclysmics, one of my favorites. I've studied them for years. Classic nova, my goodness, we know that's cataclysmic, right? It blew up, right? It's no longer around. It's a nova star, blew itself up. Did you know that there are recurrent nova? How can a nova recur? Good heavens, if it blew itself up, how can it happen again? It turns out it does. Dwarf nova? What in the world could a dwarf nova be? How could a nova be a dwarf? I thought it destroyed itself. Well, I'm going to take a little sidebar here and show you another famous dwarf nova. This is SS Cygni, and you'll see it spends most of its life at about 12th magnitude, and then in the space of about 15 or 20 hours, my goodness, it jumps up to about 8th magnitude. So it jumps about 4 magnitudes, and then over a very short period of time drops back down to 12th magnitude, and then spends most of the next 40 or 50 days at 12th magnitude, and then pow, jumps back up again. So this is a light curve of one of the most famous of the dwarf novae, SS Cygni, and you can see why they call it a novae, even though it's a small outburst. It's an outburst novae-like. And finally, supernova type 1a. This is also a variable star of some considerable interest. The bottom line on these things is that they are all binaries. There's none of these targets are single stars. Type 1a, supernovae, classic novae, recurrent novae, they are all binary systems. They are not single stars. So what in the world does a binary that can produce this kind of result look like? And here's a basic diagram. Some of you have probably seen this, but what a mess this is. This is a binary, but it's obviously not 2 stars like alcohol. It's very different than that. And by convention, over here on the left, we have a white dwarf primary. This is, remember, this is just the burned out cinder of a dead star. It's not creating new light, but it's about the size of Earth, maybe a little bit smaller, depending on the star that it came from. It's not emitting its own light. And over here on the right side, we have a K or M dwarf secondary. Now, as you know, K or M dwarfs are smaller than the sun. And in fact, this whole system as a dwarf novae, this whole system could fit inside the sun. They rotate around each other in like less than an hour, sometimes up to around 2 or 3 hours, but most of them are right around 60 to 90 minutes, and sometimes less than that. So what causes the outburst? Well, let me continue for a minute here. You might have noticed this funnel shape on the secondary. That's actually mass transfer. That's actually mass being sucked off the secondary star and flowing onto this disk, which is actually an accretion disk. This accretion disk is a swirling mass of 2,000 or 3,000 degree material off of that small dwarf secondary that's swirling around that white dwarf. So now we're going to talk about what the outburst looks like and how it occurs. And in the case of the dwarf novae, remember SS Cygni and that sudden big jump in brightness? Well, it turns out the disk goes unstable. The disk is not turning like a bicycle wheel. It's got internal friction between the various layers, and some of the material that's coming on heats up as it gets closer to the white dwarf. And the accretion disk brightens up tremendously. And when it does, you see this big jump in brightness. And some of the material pours onto the white dwarf, and it settles back down. The disk settles back down again, and you go back into the the quiescent state when the dwarf star is at its lowest magnitude again, and it stays that way until the material builds up on the disk again. Okay, now we're going to look at classic and recurrent novae. Again, it's a binary, just like the other one. The star, the secondary star may be a little bit larger and it may be a little bit farther away. But the same sort of thing happens. We have mass transfer, and eventually this disk over on the left side of the diagram starts to go unstable. And when it does, the material starts to stream onto the white dwarf. It starts to actually get sucked down into that vortex hole where the white dwarf is, and the outer shell of the white dwarf goes into a runaway nova explosion. So it turns into a kind of like a nuclear bomb. That whole outer shell starts to explode. There's a bunch of questions about, does the secondary survive? In fact, I work with one astronomer, Joe Patterson at Columbia, who's very interested in watching these classic nova in their quiescent state. You know, years and years after the nova has gone off, can we still see this remnants of this white dwarf and this secondary star? And it turns out in many cases you can. And that's what leads to the recurrence of these nova. They might take hundreds of years to go off again, but some of them do. And there's a couple of dozen recurrents that are known. Joe Patterson's interest was just that, my goodness, that secondary star survived a 100 million degree microwave oven when that nuclear explosion went off. How in the world did that poor little thing survive? Anyway, I've collected data for Joe Patterson several times. Most of these stars are really faint. So then let's talk about type 1a supernova. These are very different. Again, the secondary star is probably larger than what's shown in the diagram. And the critical difference is that the white dwarf is at a critical mass of 1.4 solar masses. Now, you may remember the Chandrasekhar back in the 20th century. He decided after reading Einstein that a white dwarf could not exist larger than 1.4 solar masses because it would collapse upon itself. So in the case of a supernova, the white dwarf in this binary pair is teetering right on that 1.4 solar mass range. And if that's big enough, when it's close enough to that 1.4 size, guess what? When that material starts to stream onto the white dwarf, guess what? That white dwarf is going to just go crazy. And the white dwarf itself is going to turn into a runaway thermonuclear explosion. The entire mass of that star is going to get involved in that explosion. So it turns into essentially an Earth-sized nuclear bomb. It's 100 times brighter than the entire galaxy that it's living in. What remains is sort of up to guesswork. Some scientists, astronomers, believe that there's still some remnants of degenerate matter, but for the most part, because of this 1 solar mass, this thing is pretty much totally involved in this explosion. So because it's 1.4 solar masses, guess what? Most of them are almost identical, to within a few percent, identical with the same brightness. And that means that the type 1a supernova are excellent distance indicators because of this known size. It's like a standard candle. These things are predictable. If you can determine the supernova is a type 1a, then you know what its brightness is supposed to be at a certain distance. Therefore, you can use it for distance calculations. And in our lifetime, this has been used to determine that the expansion of the universe is actually accelerating. This was actually a Nobel Prize back in 1998. We now know that the expansion of the universe is accelerating based on the study of type 1a supernovae. So anyway, cataclysmics are pretty interesting stuff for a lot of reasons. And I want to talk about one that was pretty spectacular that occurred a few years ago, V404 Cygni. This was a special interest for me. Anyway, it had been discovered as a nova back in 1938 on a glass plate astronomy. It reoccurred and was detected by the Ginga satellite. This is a Japanese X-ray satellite in 1989. And then in 2015, SWIFT, the NASA X-rays, the NASA satellite detected a new outburst. SWIFT was a gamma ray burster satellite detector, and it had the ability to swiftly move itself from parts of the sky to focus on a region of interest. It couldn't focus on one star, but it could get you to within a few degrees of where the outburst occurred.
Bill, you accidentally muted yourself. You have to unmute yourself, Bill. Bill, you accidentally muted yourself. You're going to have to.
Okay, is that better?
Yes, yes.
Okay. I'm not sure where I went off here, but the SWIFT satellite detected it in 2015. This was a gamma ray burst satellite that NASA had orbited. Then Integral was directed to the satellite, and redirecting Integral is a serious proposition because these big satellites are scheduled by the second. And to suddenly just to say we're going to leave behind all of its planned observations and move off to this target is a big dedication. The message boards lit up. AAVSO published some alert notices. The Japanese astronomers did the same. And it was interesting that there was, okay, I seem to have, okay, I've got another problem here of some sort. Oh, there we are. I lost my cursor, I guess. Okay, anyway, the message boards lit up and there was a high interest in visual band observations. So I got on this target and started observing it. The Integral people noted that the behavior of this source is extraordinary at the moment, with repeated bright flashes of light on timescales shorter than an hour, something rarely seen in black hole systems. In these moments, it becomes brighter than the brightest X-ray objects, up to 50 times brighter than the Crab Nebula, normally one of the brightest high energy sources in the sky. So V404 SIG became of a big interest to everyone. So as I started to observe it, well, here we go. Here's a model of what they thought V404 SIG was. And guess what? We've got another binary system. In this case, the orbiting star is, again, a small red star to the side. And the primary in this case is a black hole. It's not a white dwarf, it's a black hole. And we have an unstable illuminated plasma disk. And as the plasma starts to collapse, it goes into outburst. Here's a time series that I did on this target. And I'll point out that there's two stars plotted on this chart. This is about 4 hours of continuous observations, 60-second observations. The red line across the top is a comparison star in the field. And guess what? Over 4 hours, it doesn't hardly change at all. The black line is V404 SIG. And you can see it's changing. It drops about well over a magnitude right there on the left side of the chart. And then it starts climbing again. And you can see all this, what started to be called sawtooth behavior down in the 5 to 10 minute range. All those little peaks and valleys that were happening. Astronomers began to speculate that that was this accretion disk oscillating, showing that behavior. So this was very interesting. And I'll also point out that each of those dots has an error bar on it. So the error bars are part of this observation. So these are 60-second observations continuous over a 4-hour period. And you can see what a crazy object this thing is. Anyway, I sent my observations to the group in Japan, along with about 6 other AAVSO members sent in our observations. We all sent them all to AAVSO, but we also sent them to this group in Japan. And they ended up publishing it into a letter that got published in the journal Nature, which is one of the leading science journals in the world. So Nature actually published it back in 2016. And because of our contributions, the 6 of us that sent the data to the Japanese group are listed as co-authors. So myself and, well, let's see, Lou Cook and Michael Richmond and several others of us are actually in the co-author list on this publication. Very proud of that. So let's talk about the AAVSO in the present day. It's actually got about 1,500 members worldwide. It's got a staff of 6. We have an endowment that was left to us by a very generous member several years ago. We have an archive of over 50 million observations of variable stars. The archive is freely available to the public. Anybody can go in and look up LXSig and download observations at any time. It's part of our nonprofit purpose to help support variable star astronomy. They have online observing tools and training. So making observations, how would you do this? It's first of all important to remember that magnitudes are relative. You're not really measuring, photons per second or flux. You're actually measuring the brightness of one star compared to the brightness of another. So AAVSO, you want to compare the target to the nearby stars of known brightness. And the AAVSO publishes a whole bunch of charts of variable stars in the sky. In fact, they've got the whole sky covered. You can print charts of the entire sky. So this is an abbreviated version of what an AAVSO chart might look like. And let's say the variable star, this is obviously Auriga, and over there on the right side of the chart, you see a variable star in the field, and then you see comparison stars, a 43, a 38, and a 32. Well, those are actually the brightness of the star with the decimal removed, because the decimal might be seen as a star. So that's a 3.8 and a 3.2 and a 4.3. So this star is, and the size of the disk tells you about the brightness of the star. So if you look at that variable star, well, goodness, it's obviously brighter than the 4.3, and it's probably brighter than the 3.2. Well, is it brighter than the 2.6? Well, it might be, but it's not brighter than the 1.8. It's probably dimmer than the 1.8. So what's your estimate? What do you estimate the variable star to be on this chart? This is what visual observers do all the time. They look at a field, they look at a chart, they look at a variable star, and they gauge its brightness compared to other comparison stars on the same chart. The AAVSO's got thousands of these charts. You can download them freely and study them anytime you'd like. This is an abbreviated version. The real ones can get, you can print them to any scale and print them to any level of magnitude detail that you care to. So if you were observing variable stars visually, like I just imagined we did with that imaginary chart, what things would be of interest? Well, there's a wide range of brightness. Okay, so some of them are, well, Betelgeuse, that's well right up in the first magnitude range, and some of them are much, much fainter. We looked at LX Sig a little earlier, and it was around 14th magnitude at the bottom end. And for observing visuals, simple tools work just fine. You could have looked at that variable star in Origin with binoculars. And there are, in fact, a whole series of binocular variable stars in the AAVSO program. So you don't need a fancy telescope. You can go out in your backyard with binoculars and you can look at variable stars. Dark skies are not required. Again, you can go out in your backyard and do this. I heard Raj talking earlier about seeing M42 and M31 in his backyard. You're not looking for faint detail. You're just looking for one star or the comparison stars. How faint can you see in your backyard? Have you ever asked yourself that question? You can probably see pretty much fainter than you anticipate in your own backyard. You don't have to go to Blue Canyon to look at variable stars. You can do it in your backyard. One of the things I found is that it added structure to your observing plan. If you had a series of variable stars, let's say you had a 3-ring binder with maybe 20 variable stars in it that you kept with you, every time you go to the telescope, you can get out your 3-ring binder and look at which ones are up and make an observation and record it. And those observations are going to be useful to researchers at some point, at some time. Maybe not next week or next month, but at some point, those observations are going to be a part of a permanent digital record. There's also imaging possibilities with variables, and they call this photometry. And interestingly, most of the imaging practices that you've already developed apply. In other words, go to finding the target, tracking the target, guiding on the target, focusing on the target, all those things are exactly the same. And if you've got those things down, you can do this. You can, in fact, do this from your backyard. You don't have to go to Blue Canyon. You might be looking for a 12th magnitude target, and you don't need to go to Blue Canyon to see that. Again, dark skies are not required. You're not looking for, and I understand that imaging has the joy of looking for faint detail in galaxies or faint detail in nebulosity. That's a wonderful pursuit, and it's wonderful to get your own image that you're proud of. But you can also do a different kind of work, probably in your own backyard. If you've got it's probably not going to be true if your backyard faces a freeway on-ramp, but if you've got any kind of sky at all in your backyard, you might be able to do some work. Again, many specialized targets that I've talked about already: binary systems, long period variables, eclipsing binaries. You've got a lot of things to explore. Another thing that's a little odd is perfect focus is not always required to do photometry. Again, I know that when you're imaging, you want perfect focus on every image. Some people, when they're imaging a faint galaxy, NGC 891, they focus between every filter change. It turns out that for photometry, sometimes on a bright target, it actually works better if it's just a wee touch out of focus and just a little bit larger in diameter, because it goes on to more pixels. And sometimes the more pixels give you better photometry. Hours of image manipulation are not wanted at all. Pixel Insight, Photoshop, leave them all in your hard drive. You're not going to use them at all for photometry. In fact, it's completely discouraged. You want to take the raw measurement of the photons that hit that CCD, And you want to, because that's the science. That's the science of how many photons hit that CCD and how you're going to measure that with your photometry software. So guess what? You get to ignore all that. I take images directly out of Maxim DL right as they come out of the camera. I apply darks and I apply flats right as they come off the camera. And I don't touch those images otherwise. I do look at them because sometimes an airplane flies through the image. You're not going to be able to use that. It floods the image and saturates things. Or you get a satellite track that goes right through your image and you can't use it. So anyway, I do look at them all to make sure they're okay, but I don't manipulate and spend hours of time doing that. And the time series observations like that one I showed you on V404 SIG, that stuff is really important. Or if you're looking at eclipsing binaries, timing the minimum is important because that gives you a measure of what the period of that eclipsing binary is. And again, that's something you can probably do on a brighter target. Observations are useful to observers or to researchers. It might not be this week or next month, but eventually somebody's going to run across your observation. I also say that the AAVSO publishes alert notices of interesting objects to observe right now. We'll get into that just a little bit later. Anyway, how in the world do you get started with this? Good heavens. Okay, well, on the AAVSO website, they've got a get started menu choice, tutorials, manuals, find a mentor. There's some how-to videos, introduces many of the topics that I've talked about tonight. And over on the right side, get involved. There's some opportunities to participate with the organization. And some of this is, much of this is open to the public. Some of it requires membership. Another part of the web page is the lower down on the web page is the resources section. Here you can plot a light curve and pick a star and plot a light curve. The journal of the AAVSO is a refereed journal, published scientific articles about variable stars from the members. VSX on the upper left is a variable star index. There's 500,000 variable stars recorded there. Middle left, submit and access data. This is where you can go in and look for variable star data or submit your data if you're to the point of doing that. And over on the middle right is observing sections. I want to just show you some of the level of the observing sections that are a part of the AAVSO. Upper left, AAVSO net, there's some telescopes you can ask for time on, cataclysmic variables, a whole forum section just about cataclysmic variable observing, eclipsing binaries, there's a whole forum section for that. Exoplanets has been a big interest in the last 5 years. There's a NASA coordinator that actually works with the AAVSO now that is working on exoplanets. We actually have a separate database for exoplanet data. Interestingly, TESS is now surveying the northern hemisphere skies, and they're asking for amateur observations on TESS fields because TESS resolution is so high that even though it might detect an exoplanet, sometimes there's more than one star on the field. So they're asking amateurs to start looking at these stars and recording the ephemeris, the suspected rise and drop of field stars in those fields, because the ones that are the best targets are going to be looked at with the James Webb telescope. So this is a big area of interest in the AAVSO now. The High Energy Network has got a group of 200 variables that they suspect might be supernovas someday. They're hoping amateurs will start looking at them so that we can build a ground base of observations, prior observations, and then, I don't know, 1,000 years from now, it goes supernova, and AAVSO has already been studying that star. Spectroscopy, there's a separate database for spectroscopy now, and they've followed some of the best practices out of the British Astronomical Association about how to build that database. Solar observations, short period variables, long period variables. These are all forum topic areas in the forum section. So, plenty of opportunity, plenty of things to look at, plenty of things to get yourself involved in. And I understand that people like to go out and look at M13 every spring. I certainly do too. It's always a joy to see it. But once you've done that, maybe you've got a little inkling about trying to do some complicated observing that might have some science value to it. Does anyone use this data? This is a report that this was actually from 2017. I get one of these every week out of the database of my observations. And these, I don't know what there is, there's 10 or 12 there that were downloaded of my observations during that 1 week back in August of 17. And you can see most of these downloads are by pros. In fact, towards the bottom of the list, you can see V404 SIG. Somebody downloaded, my 2,500 observations on that target. UX UMA is on the list. BH Lin, both of those are cataclysmics. MV Lyra is a long period variable. Those are one-shot lookouts. Just look at it visually and record the observation. So yes, like I said, I get one of these every week. And in fact, some of them are 3 times this length. Some of them have 50 downloads in 1 week. So people use the data, but this data will outlive me. There's my main scope. I built a big part of the mount. There's some Byers parts there, but a lot of what you see, the gears are Byers and that declination housing is Byers, but a lot of that I built. So that's my main scope, and I've got an LX 200 12-inch that does a bunch of other stuff on long period variables. So anyway, that's my spiel for tonight. Feel free to contact me. I've worked out with Raj that I don't want to publish personal info on this talk because it's going to be up on the web. And so if you send a message off to Raj and his vice president email, he will forward to me. If you've got some questions or you'd like to get involved, you'd like to do some kind of follow-up, feel free to do so. So anyway, Raj, if you've got any questions out there, I'd be glad to, I'll leave the screen on in case somebody wants to go back to one of these slides, and I'm going to take a little drink of water too.
Hunter has 2 questions.
All right, go ahead. And also before just a minute, Hunter, anyone else also open your chat rooms, the chat room at the using the chat icon at the toolbar at the bottom of your Zoom screen. You can type a question as well. That's also a way of doing it. But anyway, let's let Hunter ask his question.
Okay, your first question is about Centaurus.
What Alpha Centaurus?
His question is Centaurus considered an eclipsing binary? No?
You said it wrong.
You say it then.
Is Alpha Centaurus considered an eclipsing binary?
No, it's not. Actually not. It is the brightest star in Centaurus. I bet you've been watching, let's see, what was the name of that program that was just on where they were traveling to Alpha Centauri, Lost in Space?
He doesn't watch TV.
Oh, okay. No, it's not an eclipsing binary that I know of. Proxima Centauri actually is an orbiting star that orbits with Proxima Centauri, and it actually gets closer to us than Alpha Centauri does.
Because each one has a second name.
Oh, he's saying that's the second name for Alpha Centauri C. I don't know what he's saying. He's saying, okay. And then his other question was about Messier 51.
That was a question.
You asked if it was, if it will turn into a chiasmatic.
It's not.
Yes, you did.
It did?
Yeah. What do you ask? Okay. Will that one turn into a to a variable star, the Catholic one?
Messier 51 is a galaxy, not a star.
I thought you. Because I'm sorry, he was just saying that it's sucking in something, and then he was talking about maybe that's kind of what it is. That's totally different. Okay.
Well, those are interesting questions, Hunter. I have to admit. Cataclysmics take thousands of years to evolve because they start out as binary stars that are very far apart. And then over time, one of them blows up and becomes a white dwarf, and then they start to merge together. So that's an interesting question, Hunter.
I actually misunderstood him, so he says I'm making him sound dumb because he. So, sorry.
No, because Messier 51 does have a companion galaxy called NGC 5195, which is almost touching one of the spiral arms of M51, and it looks like there is a bridge of material falling between the two.
Yes.
Is that what you're talking about?
So it's not a cataclysmic variable, but it is an interacting galaxy, two galaxies interacting with each other. So that's a very good question.
Okay.
Now we have some questions from Sarah. One of them is, what is the most exciting astronomical event that might happen in the next 50 years, in your opinion?
Oh, my goodness. My goodness, my goodness. Wow. I think that James Webb is going to have a series of big surprises for us. There was actually an article in Sky and Telescope last month predicting about what the biggest events would be. I would love to see another cataclysmic like V404 Cygni. that had a huge impact on astronomy. It was an excellent case where it was 12th magnitude. You could actually see that at Blue Canyon with a 3-inch telescope, and a black hole binary could actually be seen with a 3-inch telescope. That was quite an earth-shattering thing when you think about it.
Okay. Also, Sarah asks, what's a typical day like as a professional astronomer?
Oh, I think that varies a great deal. Depends on where you're working. Many of them are in the academic field. I'm not a professional astronomer by any stretch. I've all learned it's all self-taught. Most of them are academics, and most of them end up publishing work in order to maintain their academic standing. There are a bunch of professional astronomers that actually maintain telescope. Most of those are telescope operator types, or they design and build telescope. Roger Engel is the professional astronomer at University of Arizona that actually is the one that came up with the kiln that cast the 8-meter primary mirrors for the dozen or so 8-meter telescopes in the world. So it varies all over the place. A professional astronomer might be the new director of the AAVSO. The prior director has left, and now the directorship is open and available. So it varies a lot, Sarah.
All right, so now we have some technical questions about the tools of the trade from Nicholas. So is asking you, Bill, what photometry tools do you recommend? What have you used, and which ones are most acceptable to be used to enter data in the AAVSO database?
Oh,
and
boy.
Also, can you use CMOS instead of CCD?
Oh, wow, loaded question. Lots of ways to add. There are several good programs out there. A lot of people get started with AIP for WIN. That's Richard Berry's program. It does have some good photometry tools. I found myself not being comfortable with all of its aspects of operation. So I ended up moving to something called Myra. Interestingly, Myra. It's a program, it's a pay-for program that I think has some excellent photometry tools in it. I'll also say that Maxim DL, if you're using that to control your camera, actually has a pretty good photometry tool also. So you may have something you need to get you started. You can start off, you can do a time series of 100 images. You can set your target and set your comparisons. Go to the AAVSO and get a chart for the target you're working on. Identify your comp stars, identify your target on Maxim, and Maxim will run through all the images and do a time series for you and determine and produce a result that is uploadable to the AAVSO. Another one that is very popular amongst the skilled observers is called LESV photometry. It's written by a guy in Europe. It's LESVE photometry. It's actually a shareware. You can download it and use it for free. He accepts donations, but it has some wonderful tools in it. And if you're a member of the AAVSO, they have an online tool now called VPhoto that will reduce your images. And again, you can upload your images to the AAVSO and upload them into VPhoto. VPhoto will then run the reductions for you and will spit out the photometry. You can select your comparison stars and your target star directly in VPhoto, and it's free for the price of a membership. It is a membership tool, but it does a wonderful job. And I'll also add that you remember I mentioned the exoplanet group. In that group, they have another program. It's a free download called Astro Image J. It's produced by NASA. It's given to, it's part of the AAVSO exoplanet program, but it has excellent tools in it for reducing the photometry. So I do recommend trying to do your calibration images. Most of these things accept a calibrated image. So, and by calibrated, I mean dark subtracted and flat subtracted. So you have that done ahead of time. Don't bother with all the rest of that stuff. You don't want to do it.
Okay. And can you use a CMOS camera, or does it have to be
Oh,
CCD?
yeah, CMOS, heads up, CMOS is the wave of the future. It may be little known, but CCDs are a dying breed. In fact, there's no company in the US making CCDs any longer, except for specialized purposes. So what places like Maxim did is they bought ahead a whole stockpile of CCDs so that they would have them on hand. But Kodak is no longer producing them for the astronomy market. There is a company in Europe that's making back illuminated CCDs, which means they're $30,000. But CMOS is the future. CMOS is excellent. It's got some things you got to be careful with. Many of the CMOS detectors have terrible amp glow for astronomy. For pretty pictures, that can be flatted out, but in many cases, it still shows through. There are a couple of CMOS cameras that now avoid the amp glow that CMOS has. CMOS is built for, video and DSLR cameras, so it's kind of built for a different market, but people are working very hard to bring them into the market. So anyway, in fact, I've got a CMOS camera I just bought for one of my scopes, and it is, one of the other big changes is not very many of the CMOS cameras are 16-bit. Many of them are 12-bit or 14-bit, so they don't have quite the dynamic range that we're used to over in the CCD world. Over there, everything's 16-bit, so most everything is 16-bit. So yes, CMOS is a good thing to look at. In fact, there's some good discussion in the AAVSO forums about CMOS cameras. Arnie Hendon, our prior director, has been doing a lot of work with CMOS detectors, and there's a lot of good information around about them.
Okay. Dwayne has a question. This pointing out that our own sun has an 11-year cycle, and the questions are, how does that affect our sun's luminosity, and would such a cycle be visible if it occurred on other stars?
The Well, probably not, because we're talking about a millimag change, and by that mean thousandths of a magnitude. So that kind of a change is not something people would look for. There are more interesting stars to look for than the sun. So many of these binary pairs and many of these Cepheids are of big interest. And Cepheid is only, the Cepheid class is only one of about 5 or 6 classes in that instability strip on the H&R diagram. So fortunately, we are lucky that the sun is such a hum star, because it's what lets life exist on Earth. But so that kind of a change is something that we probably would not look for.
And Chuck has a question. For this kind of work, for measuring, for doing photometry, is there a preference between a color image or a black and white image?
No, all of these are black and white. Well, let me hesitate for a moment. In photometry, we do use filters, and we do use photometric filters, which are somewhat different than the RGB filters that you're using for imaging. Most of the astronomy I talked about tonight, a lot of it can be done with no filter, with a clear filter. It is recommended that you have a V filter, which is kind of like green. So for photometry, we use a BVRI series, but to get started, you really don't need to do that. You can get started by using a luminance filter as a clear filter, and maybe add a V filter so that you're in the visual band that's defined in photometry. Now, and I say that because there's 50 years of history measuring stars in that V band with photometers and actual photometers, and with CCD cameras using that filter. So your photometry that would then fit in with the 50 years of work that's been done by others.
And is there a preference? Is it better to have a monochrome camera or a color camera?
A monochrome would be preferred. Color cameras can be used, but you have to debayer the matrix, and you have to pull out the green, the red, and the blue separately. Now, again, Arnie Hendon has found that the green in a color camera can be transformed into the V band. Into the V band, yes, but the blue and the red are very difficult and just not worth the effort. So to some extent, you can use a color camera, and if you can debayer, it takes some special software to debayer. You have to know what the arrangement of your pixels are. So you can have some fun with it, and there's nothing wrong with trying it, and well, I should say, just to experiment, you can run V on a Myra class star and just see what you get. There's nothing wrong with giving it a try, but it's not the best photometry, and I wouldn't recommend that you use that data to upload, because you'd really want clean V data or clear data. So a monochrome camera would be preferred for photometry.
Okay, anyone else? Either chat room or speak now, because you now all have the power to unmute yourselves.
And I'm going to take another drink here. Well, I hope that the things I've said about setting up in your own backyard and giving your backyard a try and maybe doing some observing. I'll point out that one of the things, remember that I showed you the website where it had Get Started? There's actually a 10-star beginner's tutorial. 10 stars that beginners can start with. Some of them are binocular targets. Run out in your backyard and see if you can identify the field and print yourself a chart and give this a go. It might be better than sitting around watching a rerun of NCIS or something. Spend your evening doing something a little different.
So you're getting many accolades in the comment section from Pamela and our other members too.
Yeah, thank you very much.
Yes, wonderful presentation.
Definitely. Very, very interesting.
Would
quick
you
question.
go into outer space if you had the chance,
Oh my goodness.
recreationally?
Oh, it would be interesting to get above the Earth's atmosphere. I'll put it that way. If I could observe above the Earth's atmosphere, that would be tremendous. I don't know if I'd want to try and fly to Alpha Centauri or not, but
And another technical question from Nicholas: is vignetting an issue when you're doing photometry, and whether or not you use 32mm or 1¼ inch filters?
For visual astronomy, I would say not really. There's workarounds. If I'm understanding the question, you say 32mm, I'm assuming you're talking about an eyepiece. Basically, the task is to find the field. You know, you would print out a chart. Remember that LX Cygni I showed you early on? That long period Miro, that first light curve. You might print the chart of LX Cygni and take it out to your telescope and look through the scope. And the first problem you'd have is, which way is north? Is north up? Is it to the left or to the right? So then you would want to get your chart oriented so that it's facing the same way the view in the eyepiece is. And then you would want to see if you can spot all of the comparison stars and the variable at the same time. So most often, if you print the chart, it's going to be somewhere near the center of the field. If you can't get a very good view, well, just bump your telescope a little bit to recenter things as best you can. So again, I'm talking about visual because I kind of imagined that's what you were talking about. And no, I wouldn't use any filters for visual observing.
You're talking about vignetting.
Yes. No, I think you'd want to use an eyepiece that gave you enough of a field that you could see. And again, you're comparing one star to the other. If you can see both of them in the field well, then I think you're going to be just fine.
We're talking about photometry, vignetting.
No,
You know, which is a common. Yeah, is that a problem with filters, or is it a problem at all?
it's not a problem at all because again, you're going to center the target, and the comparison stars are going to be elsewhere in the field. So I will say that we try and size the filters so that the chip is fully illuminated. I will say that you don't want to use an 1¼ inch filter on a big chip because that would vignette the chip. So you want to have filters that fully illuminate the chip.
Thank you. Yes, and you're getting everyone from Chuck to Brian to Don to Steve. Everyone is saying thank you. Nicholas, thank you for that answer.
I guess I went down the wrong trail, not understanding the question.
No, it's okay. Everyone is satisfied with that answer, and everyone is, again, you are getting more accolades than I can mention.
Okay. One of the reasons why I encourage this backyard observing is that I know, and again, I'm not trying to take anything away from a trip to Blue Canyon, because I know that that's fun and it's an adventure all in itself. But if you're set up in your backyard, you can do the aligning and the polar alignment and all that, and then cover the scope up with a nice cover and come back to it the next night or next couple of nights. And most of that work is already done. So you don't have to recreate that setup again every time you observe. That's why I observe in my backyard, and I'm lucky to have a reasonable backyard here in Sutter Creek.